1941. America enters the war and needs to house millions of soldiers. Military bases are springing up overnight. But building traditional buildings takes months. The Navy has 72 hours to find a solution. An engineer presents a simple design, a half-cylinder of corrugated metal. The generals look and laugh. It looks like a trash can cut in half. But within 6 months, 170,000 of these cans are scattered around the world. They housed 20 million people. They cost $1,000 and were built in a day. This is the story of how an ugly idea saved the war and changed construction forever. In December 1941, when Japan attacked Pearl Harbor and the United States officially entered World War II, the country faced an unprecedented logistical challenge. Millions of men needed to be rapidly recruited, trained, and deployed. But before they could fight, they needed places to sleep, eat, and train. The problem was brutally simple, but seemingly unsolvable. How to quickly house millions of soldiers in military bases that were being built at a frenetic pace across the country and around the world. Traditional construction methods were completely inadequate for the scale and speed required. Building conventional military barracks using 1941 methods took weeks or months. Carpenters had to cut wood, construct frames, install walls, roofs, and insulation. Each building required skilled labor, specialized tools, and substantial time. And the United States needed thousands of these buildings immediately. The United States Navy faced the problem particularly acutely. Naval bases were being expanded dramatically. New bases were being built in remote locations, Pacific Islands, Arctic territories, deserts. Each new base needed complete infrastructure: dormitories, mess halls, hospitals, warehouses, workshops, administrative offices. Even worse, the buildings had to function in extremely varied climates. Freezing Alaska, where temperatures dropped to 40 degrees Celsius. Tropical Pacific, where humidity and heat were relentless. Deserts of North Africa, where scorching sun and sandstorms destroyed conventional materials. Each location presented unique challenges. Traditional building materials were also problematic. Quality lumber was in demand for shipbuilding. It was needed for ships, docks, and packing crates. Steel was being devoured by the production of tanks, ships, and weapons. Concrete required cement, which was in short supply. Skilled labor was being drained into war industries and military service. And then there was the problem of transportation. How do you ship construction materials to a remote Pacific island? Space on cargo ships was precious, needed for ammunition, fuel, food, military equipment. Wasting tons of cargo capacity on lumber and conventional construction materials was unacceptable. The Navy's Bureau of Yards and Docks was tasked with solving this impossible problem. They received a direct order in December 1941. Find a solution for military shelter that could be mass-produced, efficiently transported, quickly built by unskilled workers, function in any weather, and cost a fraction of conventional construction. Oh, and they had approximately 72 hours to present a viable concept. It was exactly the kind of impossible problem that war creates. There was no time for extensive research, careful prototyping, or prolonged testing. They needed a solution now. And that solution had to work perfectly the first time, because millions of lives literally depended on having adequate shelter. The engineers at the Bureau began working frantically. They reviewed existing designs for portable structures. They examined prefabricated constructions. They studied methods of rapid construction, but everything they found was inadequate in some way, too expensive, too slow, too heavy, too complex. The answer would come from an unexpected place and take a form no one anticipated. A form so simple, so obvious in retrospect, yet so radical for its time that it would initially be ridiculed. But this simple form, a half-cylinder of corrugated metal, would change military construction forever and leave a legacy that persists to this day. The solution came from an engineer named Peter de Jong, who worked for the Rhode Island Naval Construction Battalion. De Jong wasn't a famous architect or a renowned structural engineer. He was a practical engineer with experience in industrial construction and a mindset focused on solving real problems with limited resources. When an urgent brief arrived requesting a rapid military shelter design, de Jong began not with conventional architecture but with fundamental engineering principles. What was the strongest structural form using the least amount of material? What form could be manufactured most easily? What design would minimize separate components? The answer that emerged was surprisingly simple: a semicircular arch. In structural engineering, arches are extremely efficient shapes. They distribute weight evenly, eliminating the need for complex internal supports. A well-designed arch can support enormous loads using relatively little material. De Jong envisioned a structure that was essentially an elongated half-cylinder, a Quonset tunnel, if you will. The ends would be closed with simple walls. The ground would serve as the foundation. The semicircular shape would create both roof and walls simultaneously, eliminating complex junctions between different structural elements. For the material, de Jong chose corrugated steel. Corrugated steel, sheets of metal with pressed-in corrugations, had marvelous structural properties. The corrugations dramatically increased stiffness without adding significant weight. It was like turning flat paper into cardboard. The corrugations created structural strength. Crucially, corrugated steel was relatively abundant. It wasn't the high-quality steel needed for tank armor or ship hulls. It was commercial steel that could be produced by existing metal mills without diverting resources from critical weapons production. De Jong's design was radical in its simplicity. The structure would be composed of interlocking, arched, corrugated steel panels. Each panel was approximately 4 feet wide. You would assemble them side by side, bolting adjacent edges together until you had a tunnel of the desired length. Then you would close the ends with simple walls, including doors and windows. There was no complex internal structure. There were no beams, columns, or trusses. The arched steel shell itself provided all the structural strength. It was monocoque, an aviation term meaning that the outer skin carries structural loads like an airplane fuselage. The floor would simply be poured concrete or wood laid directly on the leveled ground. Insulation could be added by lining the interior with fiberglass or other materials. Heating and electricity could be installed via simple conduits. When de Jong presented his designs to his superiors at the Bureau of Yards and Docks, the initial reaction was unfavorable. Officials looked at the simple semi-cylinder and saw not dignified military architecture, but something that looked like a giant trash can cut in half. It was ugly, had no architectural precedent, and looked completely unmilitary. "It looks like something you'd keep garden tools in," an officer commented sarcastically. "Do you really expect us to house American sailors in that?" But de Jong had numbers on his side. He calculated that a structure 16 feet wide by 36 feet long could be manufactured using approximately $600 worth of materials. It could be assembled by 3 unskilled men in less than a day using only basic hand tools. It would weigh approximately 9,000 pounds, enough to fit in a single railroad car or cargo ship's hold. It could comfortably house 8 men or serve as a warehouse, workshop, or administrative space. Most importantly, the design could be put into mass production immediately. Existing metal factories could begin producing panels without significant retooling. No skilled labor would be required for manufacturing or assembly. Despite initial skepticism, the urgency of the situation forced the Bureau of Yards and Docks to give the green light to de Jong's project. In January 1942, just weeks after Pearl Harbor, the first prototype was built at the Naval Construction Battalion Center in Davisville, Rhode Island, a location that would give the design its name, Quonset Hut, after nearby Quonset Point. The prototype was deliberately built under adverse conditions to test the viability of the concept. Rhode Island winters were brutal. Freezing temperatures, strong winds, frozen ground. If the design worked here, it would probably work anywhere. The assembly team consisted of 3 sailors with no prior construction experience. They were given arched corrugated steel panels, fastening hardware, basic hand tools, and simple instructions. The clock started. The panels were surprisingly easy to handle. Although each weighed approximately 150 pounds, 2 men could lift it comfortably. The panels had pre-drilled flanges along the edges where screws would connect them to adjacent panels. It was simple mechanics. Lift panel, align with previous one, insert screws, tighten. The foundation was equally simple. The ground was roughly leveled. Wooden beams were placed as a base on which the edges of the arched panels would rest. There was no need for an elaborate concrete foundation or deep piles. The weight distribution of the arched structure meant that pressure on the ground was relatively low and evenly distributed. The arched panels were erected sequentially, starting from one end. Each new panel was bolted to the previous one. As more panels were added, the structure became progressively more rigid. When the 10th panel was installed, completing the 40-foot structure, it was surprisingly strong. It could support a man walking on its arched roof. The end walls were then installed. They were simply flat panels of wood or metal with openings cut out for doors and windows. Doors and windows were standard, commercially available components. Nothing had to be custom-made. The roof didn't need any additional materials because the arch structure itself was the roof. This completely eliminated one of the most complex and time-consuming aspects of conventional construction. There were no tiles, ceiling beams, or roof framing to build. In approximately 10 hours of work, the first Quonset hut was complete. 3 unskilled men, using only hand tools, had built a fully functional structure in less than a single day's work. Observers were impressed. The next test was functional. The hut was fitted with a basic wood-burning stove for heating. Fiberglass insulation was installed lining the interior. Wooden flooring was laid. Bunk beds, tables, and basic equipment were moved inside. For several weeks during Rhode Island's brutal winter, volunteer sailors lived in the Quonset hut to test real-world conditions. They reported that the structure was surprisingly comfortable. The stove heated the space efficiently. The arched shape meant that hot air circulated well. Strong winds were no problem. The aerodynamic shape deflected gusts with minimal structural stress. Heavy snow accumulated on the arched roof without causing problems. In fact, the arched shape was ideal for snow loads. Weight was distributed evenly without creating concentrated stress points. In contrast, flat or pitched roofs of conventional buildings often collapsed under heavy snow. Rain testing revealed an unexpected benefit. Water simply ran down the arched roof without pooling. There was no need for complex gutters or drainage systems. And because the seams between panels ran vertically along the length of the structure, leaks were rare even with imperfect sealing. With the prototype proving successful, the Bureau of Yards and Docks moved with remarkable speed to mass production. In February 1942, contracts were awarded to multiple metal fabricators across the United States. The specifications were deliberately simple so that any factory with metal forming equipment could produce components. The George A. Fuller Company of New York became the main manufacturer, but dozens of other producers were quickly brought in. Strand Steel Corporation, Great Lakes Steel, Armco Steel, companies that normally produced industrial metal products, were converted to production at Quonset hut. The manufacturing process was surprisingly straightforward. Flat sheets of 20-gauge steel, approximately 0.0035 inches thick, were fed into corrugating machines that pressed in the characteristic corrugations. The corrugated sheets were then fed into forming presses that bent them into precise arcs. Edges were folded to create flanges with pre-drilled holes for screws. Each panel was galvanized, coated with zinc to prevent rust. The entire process from flat sheet to finished arched panel took approximately 20 minutes per panel on an optimized production line. Standardization was key to mass production. Initially, 3 standard sizes were established: 16 feet wide by 36 feet long, the most common, 20 feet by 48 feet, and 40 feet by 100 feet for large warehouses and workshops. Each size used identical panels. Only the number of panels varied. This meant that factories could produce single panels of any size and shape and be manufacturing components for all 3 frame sizes. Economies of scale were enormous. By mid-1942, factories were producing over 1,000 Quonset huts per week. The cost dropped dramatically with production volume. The initial prototype cost approximately $1,000 in materials. By June 1942, with full mass production, the material cost for a 16x36-foot hut had fallen to approximately $600. In 2024 dollars, that's approximately $11,000, extraordinarily cheap for a fully functional structure. Compare that to the cost of building a conventional military barracks of similar size, which was approximately $3,000 to $4,000 in 1942. Quonset huts cost 1/5 to 1/6 of what conventional construction cost, and they could be built in a fraction of the time. The shipping packaging was another triumph of efficient design. A complete 16x36-foot Quonset hut kit, all steel panels, hardware, doors, windows, and instructions, would fit into a single wooden crate measuring approximately 6 feet by 4 feet by 8 feet. Total weight was less than 10,000 pounds. This meant that a complete Quonset hut could be transported in a single railway wagon or in the hold of a cargo ship. Multiple huts could be stacked efficiently. Cargo space that could carry 5 or 6 huts would transport materials for perhaps a conventional building. For overseas military installations, this transportation efficiency was revolutionary. A standard Liberty ship could carry approximately 500 Quonset huts in its cargo. This represented accommodation for approximately 4,000 men, or space equivalent to dozens of warehouses and workshops. Previously, even fracturing this infrastructure capacity would have required multiple ships loaded with conventional construction materials. Assembly instructions were deliberately simplified. Complex technical drawings were replaced with step-by-step illustrations that any literate person could follow. Each panel was numbered. Instructions simply stated, "Connect panel 1 to panel 2 using the supplied screws." It was essentially IKEA assembly on a massive scale, decades before IKEA existed. Between 1942 and 1945, approximately 170,000 Quonset huts were produced and deployed virtually worldwide. They appeared in every theater of operations, in every imaginable climate, serving hundreds of different purposes. The versatility of their simple design proved to be one of their greatest strengths. In the Pacific, Quonset huts sprouted up on countless islands. Guadalcanal, Iwo Jima, Okinawa, the Philippines. Each island captured from the Japanese quickly saw American bases established, and these bases were constructed almost entirely of Quonset huts. Tropical heat and humidity that would rot wood in months barely affected galvanized steel. Seabee combat engineers became experts at building Quonset huts under impossible conditions. They constructed them on sandy beaches, in dense jungles, on rugged volcanic terrain. In some cases, huts were erected while combat was still raging miles away. Speed of construction meant that infrastructure could follow fighting troops almost immediately. In North Africa and the Middle East, Quonset huts faced scorching heat and sandstorms. The design proved ideal. Sand simply slid off the curved surface. The interior remained relatively cool because the steel reflected solar heat. When insulation was added, the internal temperature dropped significantly below the external temperature. In Europe, tens of thousands of Quonset huts were built in England as part of the build-up for the D-Day invasion. Entire air bases consisted primarily of Quonsets: crew dormitories, briefing rooms, administrative offices, equipment warehouses, even chapels. The RAF was so impressed that it adopted the design for its own use under the name Modified Nissen Hut. In Alaska and the Aleutians, where temperatures dropped to 40 degrees Celsius and winds exceeded 100 millimeters, Quonset huts proved surprisingly resilient. Heavy insulation was installed, sometimes with a second layer of panels creating a double wall. Snow accumulated on the arched roofs, but distributed weight evenly without causing structural collapse. Uses were incredibly diverse. Although primarily designed as dormitories, Quonset huts were adapted for virtually every imaginable use. Field hospitals used multiple connected huts, one for triage, one for surgery, others for recovery. Aircraft hangars were built by connecting 40-foot huts side by side, creating enormous spaces. Movie theaters were created in large Quonset huts, providing critical entertainment for troops. Chapels allowed for religious services. Libraries and recreation rooms offered stress relief from combat zones. Officers' clubs and NCO facilities were established. Even morgues and remains storage facilities used Quonsets. The versatility extended to modifications. Windows could be added at any point by cutting openings in the steel and installing frames. Ventilation could be improved by installing vents in the ceiling. Internal partitions created multiple rooms. Extensions could be added by bolting additional huts in sequence, creating structures of any desired length. In some cases, Quonset huts became semi-permanent structures with substantial improvements. Concrete was poured for floors. Complete insulation and interior cladding created comfortable environments. Sophisticated heating and ventilation systems were installed. Some huts even received false interior wall panels that made them look like conventional buildings inside. Soldiers developed a love-hate relationship with Quonset huts. They were undeniably functional and far superior to tents or no shelter at all, but they were Spartan, echoed loudly, and in winter could be freezing despite heating. Moisture would condense inside the steel roof and drip onto occupants. In summer, they could become ovens if not properly ventilated. As Quonset huts were deployed in diverse environments, users developed countless modifications and improvements. The basic design proved to be a remarkably adaptable platform that could be customized to specific needs. Some of these innovations were officially adopted, while others remained creative field modifications. One of the most common problems was temperature control. In hot climates, the steel roof acted as a huge absorber of solar heat, turning the interior into a sauna. Engineers developed several solutions. Painting the exterior with reflective white or aluminum paint significantly reduced heat absorption. Installing reflective insulation under the steel roof created a radiant heat barrier. In some tropical bases, a second canvas or metal roof was installed a few feet above the actual Quonset hut, creating an air space that insulated the structure below. This technique, borrowed from colonial architecture, proved highly effective. Ventilation was improved by installing louvers, ventilated openings, in the end walls that allowed cross airflow. For cold climates, the challenge was to retain heat while preventing condensation. Insulation was essential. Fiberglass was most common, but straw, sawdust, and even old newspapers were used in desperate situations. Vapor barrier, plastic sheeting or tarred paper, was installed between the insulation and the interior to prevent condensation of moisture. Heating systems varied enormously. Wood-burning stoves were most common where firewood was available. Oil heaters were used in remote locations where liquid fuel could be transported. Some larger bases installed central heating systems with ducts running through multiple huts. In one notable case in Alaska, engineers diverted steam from a power plant through underground ducts to heat dozens of Quonset huts. Foundations also saw substantial innovation. While the original design simply rested on level ground, users discovered that elevated foundations significantly improved comfort and durability. Raising the hut on a wood or concrete foundation created crawl space that insulated the floor from cold or damp ground and allowed access to plumbing and wiring. In areas with permafrost or unstable soil, engineers developed stilt foundations that distributed the weight of the structure without affecting the frozen ground. In earthquake zones, ground anchors were added to prevent movement. In flood-prone areas, huts were built on elevated platforms. Connections between multiple Quonset huts created interesting architectural possibilities. Creative officers connected huts in T, L, or even H-shaped configurations, creating complex layouts. Huts could be stacked 2 or even 3 high, with stairs and corridors connecting levels. Some bases created substantial office buildings by connecting dozens of huts in grids. Door and window modifications were common. While standard designs had a single door at each end, users frequently cut additional side doors for better access. Windows were added along the sides, a simple process of cutting an opening, framing, and installing standard glass. Some huts received skylights by cutting openings in the arched roof. Specialized functionality led to unique adaptations. Hospitals required abundant natural light, so medical huts often received extensive windows and even translucent fiberglass sections in the roof. Photographic laboratories needed complete darkness, so all openings were sealed and double light entry was built in. Aircraft repair facilities needed extremely wide doors to move planes in and out. This was achieved simply by making the entire end wall a massive sliding door. Ammunition depots received extra reinforcement and were partially buried underground for protection against accidental explosions. It is difficult to overestimate the impact of Quonset huts on the American war effort. They solved a critical logistical problem that could have severely compromised military operations. Without them, building the infrastructure needed to support millions of soldiers globally would have taken years and consumed vastly greater resources. Consider the numbers. 170,000 Quonset huts, produced between 1942 and 1945, provided approximately 20 million square feet of covered space. If that space had been built using conventional methods, it would have cost approximately $500 million in 1945 dollars, over $8 billion in 2024 dollars. The actual cost was a fraction of that, saving resources that could be directed toward the production of weapons, ships, and aircraft. More important than cost was time. Building equivalent infrastructure conventionally would have required hundreds of thousands of skilled carpenters working for years. Skilled construction workers were scarce, needed for shipbuilding, aircraft production, and other critical war industries. Quonset huts could be assembled by anyone with basic strength and the ability to follow simple instructions. This freed up skilled workers for more critical tasks, while allowing unskilled men to contribute significantly to the war effort. Seabees, the Navy's construction battalions, included many men with no prior construction experience, but they could build entire bases using Quonset huts in weeks. Speed of deployment also had a direct strategic impact. When Marines captured a Pacific island, Seabees often landed with them or immediately afterward. Within days, a functional airbase existed where before there was only jungle. Bombers could operate, fuel could be stored, troops could be comfortably housed. This ability to rapidly establish advanced infrastructure enabled the island-hopping campaign that defeated Japan. Each captured island became a base for the next attack. Without Quonset huts, building each base would have taken weeks or months longer, dramatically slowing the operational pace. In Europe, the massive concentration of forces in England before D-Day was facilitated by Quonset huts. Millions of American soldiers were housed, trained and equipped in bases that were built in months. Entire air bases of B-17s and B-24s operating strategic bombing against Germany were supported by Quonset hut infrastructure. After D-Day, as Allied forces advanced through France and into Germany, Quonset huts followed. Evacuation hospitals were established in huts. Supply depots, vehicle repair shops, communication centers, critical infrastructure could be established in days instead of weeks. The psychological benefit should not be underestimated. Soldiers fighting in miserable conditions on the front lines had some comfort in knowing that when they returned to the rear, there would be adequate shelter. Quonset huts were not luxurious, but they were infinitely better than tents or sleeping outdoors. Morale matters in war, and even small improvements in living conditions affect morale. Soldiers who could sleep dry, warm, and relatively comfortably fought better than those who were constantly miserable. Quonset huts provided this basic comfort for millions. For medical personnel, Quonset huts were literally lifesavers. Field hospitals in huts provided a sterile, dry and protected environment for surgery and recovery. Compared to the medical tents that were previously standard, huts were vastly superior. Countless soldiers survived injuries because they could be treated in proper medical facilities near combat zones. Quonset huts' contribution to the Allied victory will never be precisely quantified, but it is clear that they solved a critical problem exactly when it was needed. They exemplified American ingenuity, practical thinking applied to a real problem, resulting in a solution that was simple, effective, and scalable. When World War II ended in 1945, the United States military possessed approximately 150,000 Quonset huts scattered globally. Bases were being closed, troops were being demobilized. The question was, what to do with all these metal structures? The answer would transform Quonset huts from a temporary military solution into a lasting civilian architectural phenomenon. In one of the largest surplus disposal programs in history, the US government began selling Quonset huts to civilians at absurdly low prices. Huts that cost $1,000 to produce were sold for $50 to $200. Returning veterans with GI Bill benefits but limited income were the primary buyers. Young families desperate for affordable housing discovered that Quonset hut could be transformed into a surprisingly comfortable home with some creativity. Cost was a fraction of conventional housing, and they could be erected on weekends with the help of friends. Entire subdivisions of Quonset huts sprang up near military bases and in metropolitan areas. These Quonset villages were often blended communities of veterans and young families. Residents customized their huts extensively, adding partition walls, installing plumbing and wiring, building extensions, planting gardens. Some conversions were remarkably sophisticated. Creative architects recognized that semicircular structures created interesting interior spaces. Vaulted ceilings made small huts seem more spacious than rectangular buildings of similar square footage. Exposed arch beams could be left visible for an industrial aesthetic effect. Universities facing an influx of veteran enrollments, using the GI Bill, purchased hundreds of Quonset huts for temporary dormitories, classrooms, and administrative facilities. Temporary often turned into decades. Some campus huts remained in use well into the 1980s and 1990s. Students developed a nostalgic affection for these unconventional buildings. Farmers found Quonset huts ideal for grain storage, equipment shelter, and even stables. The arched shape meant there were no interior columns taking up space. Trucks and tractors could easily enter and exit. Grain stored in huts remained dry. Cost was a fraction of a conventional barn. Businesses enthusiastically embraced Quonset huts. Auto repair shops, small factories, warehouses, even restaurants and bars were established in surplus huts. In rural areas where zoning codes were lax, Quonset huts became ubiquitous commercial architecture. They were inexpensive, quick to build, and fully functional. Rural churches, especially denominations with limited resources, used Quonset huts as temporary or permanent places of worship. The acoustics of the arched structure were actually quite good for music and speaking. With properly finished interiors, huts could be dignified and comfortable worship spaces. Recreational clubs and community organizations used Quonset huts for meeting rooms. Veterans of foreign wars, VFW posts and American Legion halls were frequently established in surplus huts. Small community centers, especially in rural areas, adopted the design. It wasn't just in the US. Surplus Quonset huts were transported to dozens of countries. Some were donated through foreign aid programs, others were sold. They appeared in post-war rebuilding Europe, Latin America, and Asia. In some countries, they became so common that they were considered local architecture. Commercial production of Quonset-style structures continued well after the war. Companies recognized continued demand for inexpensive, prefabricated, and quickly constructed buildings. Designs were refined, improved insulation, better windows, more attractive doors, but the basic form remained unchanged. In the 1950s and 1960s, Quonset huts were a common part of the American landscape. Practically everyone lived in, worked in, or visited one at some point. They were particularly prevalent in rural and sprawling suburban areas, where quick and cheap construction took precedence over conventional aesthetics. Although Quonset huts were designed purely for function without aesthetic consideration, they inadvertently influenced modernist architecture and design thinking in surprising ways. The stripped-down utilitarian design resonated with architects exploring minimalism and structural honesty. Modernist architects of the 1940s and 1950s were fascinated by the pure form of Quonset hut. It was a structure that was exactly what it needed to be. Nothing extra, nothing decorative, just efficient form-serving function. This aligned perfectly with the modernist dictum, form follows function. Buckminster Fuller, the visionary architect famous for geodesic domes, studied Quonset huts extensively. He appreciated how the arched structure efficiently distributed structural loads, minimizing material while maximizing strength. Principles he learned from Quonset huts informed his own revolutionary designs. Influential designers, Charles and Ray Eames, used surplus Quonset hut as a studio in the 1940s. They appreciated the honesty of design, exposed steel structure without architectural pretense. This aesthetic influenced their furniture design and overall approach, which emphasized honest materials and functional forms. The tradition of prefabricated construction that Quonset huts pioneered continued to evolve. The 1950s saw an explosion in prefabricated and modular homes. While most did not use an arched form, they shared Quonset's principles: factory manufacturing, quick assembly, low cost, and standardization of components. Tension structures, such as fabric tents and stretched membranes, gave Quonset huts credit for demonstrating that monocoque shell structures could be practical for construction. The principle that the outer skin carries structural loads became more widely accepted in part because Quonset huts proved to work. In recent decades, there has been a resurgence of interest in Quonset huts among sustainable architects and builders interested in energy-efficient construction. The arched form has proven surprisingly good for energy efficiency. Less external surface area relative to internal volume compared to rectangular structures means less heat loss. Green home builders have rediscovered Quonset huts as a platform for sustainable construction. Durable steel framing can last for decades or centuries with minimal maintenance. Modern spray foam insulation can create a highly efficient building envelope. Solar panels are easily installed on the curved roof. Many modern Quonset homes are net zero energy. The tiny house community has also embraced Quonset's design. Small huts, 12 or 16 feet wide, can be transformed into comfortable minimalist homes. The absence of interior columns maximizes usable space. Arched design creates a sense of openness that would make an equivalent rectangular space seem cramped. Modern farmers still use Quonset huts extensively. New designs incorporate improved ventilation, larger doors, and superior insulation, but the basic form remains unchanged from the 1941 design. They are still the most economical solution for large covered storage in agricultural settings. Industrial and commercial facilities continue to utilize Quonset-style structures. Warehouses, manufacturing workshops, distribution centers, any application requiring large open interior space without obstructive columns can benefit from arched design. Modern metal building companies offer structures essentially identical to the original Quonset huts, only with updated materials and finishes. The historical preservation of original Quonset huts has become a cause for some enthusiasts. Remaining examples from the W. era are increasingly recognized as valuable cultural heritage. Some have been listed in historical records. Museums have included preserved Quonset huts as part of exhibits on wartime life. Perhaps its ultimate tribute is that its form is instantly recognizable decades later. Say Quonset hut to virtually any American above a certain age, and they'll immediately picture the distinctive semicircular shape. Few architectural designs achieve such universal cultural recognition. The story of Quonset hut offers remarkably relevant lessons for design, engineering, and innovation today, more than 80 years after its creation. It is a case study in how necessity breeds innovation and how simple solutions can overcome complex designs. The first lesson is about the power of constraints. Quonset hut was designed under extreme constraints: limited time, scarce materials, unskilled labor, the need for efficient transportation. These constraints did not inhibit innovation, they forced it. When you can't use conventional solutions, you must think fundamentally differently. Modern designers often work best when they have clear constraints. Unlimited budget and unlimited time often lead to design bloat, unnecessary features and complexity. Constraints force ruthless prioritization. What is absolutely essential? What can be eliminated? Quonset hut is a perfect exercise in essential design. The second lesson is about the elegance of simplicity. Quonset hut had no unnecessary components. Each piece served a purpose. The arch was simultaneously wall, ceiling, and supporting structure. There was no decoration, no artificial architecture. It was pure function manifested in form. This honesty of design is increasingly valued today. Consumers appreciate products that are what they appear to be, where form clearly expresses function. The minimalist aesthetic that Quonset huts exemplify has become mainstream in product design, architecture, and even software UI. The third lesson is about the importance of rapid prototyping and testing. Quonset hut went from concept to functional prototype in weeks. It was tested under real-world conditions, adjusted based on feedback, and put into mass production in months. There were no years of research and development or prolonged testing. This echoes the modern MVP, minimum viable product approach. Build something functional quickly, test it in real-world conditions, learn from what works and what doesn't, iterate rapidly. Quonset hut proved this approach decades before it became startup doctrine. The fourth lesson is about the power of standardization. All components of Quonset hut were standardized. Panels were interchangeable, hardware was identical, instructions were universal. This allowed for mass production, simplified training, and easy maintenance. Standardization is sometimes seen as the enemy of customization and flexibility. But Quonset huts proved that standardized design can be a platform for infinite customization. The basic structure was always the same, but users adapted it for thousands of different uses. This is the platform design philosophy that drives successful modern technology products. The fifth lesson is about the value of democratic design. Quonset huts were designed to be built by anyone, not just experts. Instructions were simple, tools were basic, technique was straightforward. This democratized construction, allowing ordinary people to create permanent shelter. Design that empowers users instead of requiring reliance on experts has a profound social impact. Open source software, DIY architecture, the maker movement, all share this ethos of accessible design that anyone can use and adapt. The final lesson is about humility and pragmatism. Quonset huts were initially ridiculed as ugly and undignified, but they proved to be exactly what the situation required. Conventional aesthetics and architectural prestige were irrelevant. It worked, and that was all that mattered. There is wisdom in focusing on effectively solving real problems rather than pursuing elegance or sophistication for their own sake. The best solutions are often not the most impressive or aesthetically pleasing. They are the ones that work reliably, cost reasonably, and can be implemented widely. Quonset hut, that rejected garbage can, ended up housing over 20 million people, serving thousands of purposes, lasting decades beyond its intended lifespan, and influencing architecture to this day. Not a bad legacy for a design that took weeks to develop under desperate wartime pressure. Sometimes the best solution is the one everyone initially dismisses as too simple. But as Quonset hut proved, simple works.